The following is going to be a conversation about quantum machine learning, applications in the finance sector, academia, research, life, and much more with Dr. Xavier Mancilla Montero, a researcher in quantum machine learning with his PhD in quantum computing and founder and CEO of Falcondale. Also, folks, if you're interested in such deep science and deep tech conversations and are able to garner even the slightest bit of value from the show, please support us by clicking the subscribe button so that we can keep improving the quality of the videos and keep on having such wonderful guests over for you. Furthermore, comment down below your favorite matters of discussion in the quantum realm, science, technology, each and everything. Now, without any further ado, let's get right into it. Enjoy and thank you. Okay, we are rolling now. So, from what I understand about your background, you transitioned into quantum computing from machine learning, right? You had an expertise in machine learning, and then fascinated by the matters of quantum mechanics, you transitioned into the entire domain of quantum computing and overarchingly quantum machine learning, rather. What exactly is quantum machine learning? Like, surely it takes machine learning up a notch, or maybe in a different perspective, all in general. But for the common folks, what exactly is quantum machine learning?
The way that you describe my journey to quantum is accurate. So I started with machine learning projects in several industries, but mainly in the finance sector with great scoring. Um, and I always was curious about two things that at the end of the day will merge in one single thing. That is, I was curious about how the universe works, right? How everything is made up by atoms at the end of the day, and it's not exclusive this for QML or in quantum technology. It's about the reality that we are looking every day, right? So in that sense, I was curious about this field, and at the same time, I think that at some point the machine learning approaches, specifically in the classification part, which is my field, um, you always have some difficulties to keep increasing once you have everything in place with the minimum requirements. So you're trying to optimize parameters, you use XGBoost, which is a technique of classification with gradient boosting, or you use logistic regression, or you use any other like kind of classical approach that the banks or fintechs or even any industry is using for classification. But when you reach certain AUC, a certain performance, you start looking at something else. Should be deep learning, should be, I don't know, neuromorphic technologies or inspiration in neuromorphic. Uh, so at the end of the day, it's like unconventional computing. So what else is there? What we can find there? And I certainly became fascinated by the quantum field in general, quantum mechanics, quantum principles, and I started studying, I guess more like 5 to 6 years ago, more deeply. Okay, what I can extract from the quantum principles and the quantum mechanics to actually increase the quality of those models that they reach some certain point, certain Barren plateau that is not increasing. Eventually, you need to extract more data. So trying to grab better data sources, better information to actually create better models, but at some point is kind of stuck. You cannot have any progress. So I start testing with quantum, um, and exactly what you said about how you can jump from machine learning to quantum machine learning is trying to understand. So you asked me how you could explain quantum machine learning. It's actually something that I tried to explain in my last book, which is QML Unlocked, and it's available in Amazon. Is exactly how I will explain to others how this works. And it's difficult to answer you this in 1 minute, but mainly it's like using the quantum principles of entanglement, interference, and superposition to create a representation of the data that is different than classical models. Mainly, you will say that in optimization, you have the benefit of using qubits and the superposition entanglement principles to actually scale and be able to represent more data, let's say simultaneously for easy understanding. But also in the field of QML, when you use quantum kernels, you are using a representation of the data that is quite different in a different dimensionality, which is the Hilbert space at the end of the day. So it's not only about how simultaneously you can represent data, which is the typical explanation about optimization, for example. It's also about in QML how you can represent the data easily so we can separate the data at the end better. um, Imagine that you have dots, right? So you have red dots, which is people that not pay their loans, and blue dots that actually pay. But in the market, they are really mixed up. If you have a two-dimensional chart or a plot, and you can see that they're not easy to separate. Eventually, you have some a specific variable that is extremely good and allows you to separate this better, but it's not common. So you need to have better models to represent the data in a way that can be separated by a line, or let's say a hyperplane, and using a classical SVM once you have the quantum kernel representation to separate this better. So in QML, it's not only about using entanglement and superposition to scale like the optimization process, which is useful even for feature selection. Optimization is quite good. But for the QML itself, the classification is really interesting how you can represent the data differently. And the other thing for classification on QML that is really relevant or is promising, but there's some concerns about Barren plateaus, is using variational classifiers, which is a way to basically have this loss function system to iterate between a quantum circuit and a classical computer and reparameterize these parameterized quantum circuits. And at the end of the day, you have the best performance during this process of let's emulating a neural network with a variational classifier. And then you have the promising result using again qubits and all the properties of quantum machine learning, let's say quantum principles and the quantum machine learning as a technique. So I would say that there's a lot of work for the, I don't know, not only a few years ago, but mainly I would say 10 or more years ago, trying to create something meaningful from these techniques. And my concern also is keep improving the way that we create algorithms, because we're using those quantum principles for these techniques that I just mentioned, but eventually we need new algorithms completely from scratch, because you say that we share that the QML part in the technique of kernels and in the technique of variationals, they are quite inspired in the classical methods. It's like a variation of what we already have. So the idea is to understand how much we can extract from these principles and benefits from quantum, and in a way that eventually is not classically made anywhere. So this is something that we need to keep testing and evolving with the devices that are available, with the simulators and emulators that are available, and see what we can do in the following months or even years.
To just better understand the entire domain's subject matter, what to what extent are we able to do whatever we want to do in regard to the capabilities of quantum machine learning and quantum technology in general? Like, there is the hype part, like there is hype, then there's hope in certain areas, and then there's the current reality. Like, what is it?
Yeah. One of the things that I try to always share in these conversations is that you can do something with quantum techniques today. Okay. And this will probably not work in NISC devices or the noisy quantum devices that we have available these days. Or if you can do something, you need to put a lot of effort, and eventually you will have a very narrow and a specific case that could work. But my approach for the last, let's say, 2-3 years is design something that is pointing to the next machines, but just working, being executed in simulators for the problem of the noise. Of course, this is limiting the capacity of scaling, because you know that you cannot simulate more than 20, 30, or even 40 something qubits in a classical computer. It's unfeasible to reach more than that. So what I'm always trying to do is trying to bring this to the market, and my way to bring this to the market is program everything for a niche machine, but just simulating. And we are testing that in several financial institutions in Latin America, here in Europe, and in several, let's say, levels of companies, from the smallest one and up to the bigger, um, that there's some non-linearity in the data sets that they're using in terms of how you can separate the classes that can be addressed by a more complex quantum circuit in the sense of feature maps or the kernels. So it's working, and it's giving you better AUC, eventually 2, 3, 4 percentage points better, which you can say is really small. But for business like in the finance sector, it could be millions of dollars yearly, right? So for the people that don't understand what is AUC, is basically the quality of the model between zero point 0.5 and 1. And if you increase 2, 3, or 5 percentage points, this could mean that you can approve more people with less risk or stop more people that actually are not good enough to receive a loan. So what I'm seeing is that uh, if we have better models, let's say algorithms in the following months, and the devices, and we find a way to have better quality of qubits, and the way that we program on those devices is more, let's say, reliable, we can have even better results quite faster. So my prediction in that sense, and it's not only in the finance sector, I would say this is in chemistry, in optimization in general, let's say logistics, or I don't know, drug discovery, is that very soon we will find a way to fit those problems in the quantum devices, and we will have some kind of ChatGPT moment, but smaller, let's say, but significant for especially for the industries. And they will start like scaling all the things that they're already there. So I'm not the only one trying to play with some algorithms and see if simulating this stuff is working. But there's a lot of companies in the software side or even vendors of quantum hardware that are trying to create their own layers of software to actually bridge this gap between the hardware and the practical application in the industry. So I would say that we are close to do something meaningful. And if someone asked me, okay, you can do something with quantum devices today, I would say probably no. But you can simulate something meaningful from quantum techniques, I would say yes. And I can prove that. So it's really interesting to keep testing, but the end game is not just simulating and see a few percentage points better, which is okay, but the main goal is using quantum devices, and we need to keep attention of everything that very talented people is doing in the industry of devices, and see what we can get in the following months.
With so much going around in the world in the domain of research, development, science, technology in general, it is sort of invariable to feel like things that you really did not expect to come into fruition, into the material reality, just happen. Like, the future may be coming a little too early. For me, for example, uh, talk about something like chat gpt being a completely generative AI just coming out of the market. We used to watch Iron Man movies and the entire notion of having Jarvis there with Tony Stark. I mean, people used to do make projects around that, engineering students, right? It was an inspiration for most people to get into that stuff, programming and everything. But having it out to the people, for the people, at such a large and accessible extent, I mean, it was just like close to a very unexpected miracle of sorts. When it, for the first time, when it was introduced, what was one moment, or maybe few moments, howsoever they were for you, where you felt that okay, maybe the future came a little early than I had expected it?
Yeah, when even I think related to quantum computing, I think when I start investigating how this works and how this starts at some point, of course, we can talk about, I don't know, 100 years of history about this, even from Einstein and Niels Bohr and a lot of great people in the history of quantum in general and quantum computing from Feynman onwards. But the great discovery perhaps is the short algorithm, right? This like creates the spark to keep evolving and testing stuff and see how we can get the point, or we can reach the point to actually run this algorithm in a scalable way. And this will mean something encryption and security and a lot of things. But personally, when I start thinking or investigating about quantum computing, and I was just related to machine learning, the way that this system works is already amazing. And I think no one is paying attention to that. So we are playing with subatomic particles. We are playing with atoms. We are trying to manipulate this with lasers, with pulses, with, I don't know, several technologies that there are several qubit technologies or QPUs technologies, let's say, ions, neutral atoms, superconducting in general. So, um, and this is surprising for me already. So it's not the ChatGPT moment that you're mentioning, because I think this will happen in a few, let's say 2-3 years, I guess, in a smaller scale. I will not say that everyone will start programming like or using quantum computing in 24 months or something, which is the case of OpenAI's ChatGPT, and suddenly everyone is using ChatGPT like Google at some point. But in the case of industry, I think this will have a huge impact, and I'm already impressed about what you can do with those small particles, and talks a lot about how the humanity can evolve. So I think it's already amazing. In terms of this ChatGPT moment in the future, I think again will not impact all the people, but I think all the people should be aware of what is happening. Um, I mean, the current people that are studying in the universities or in the schools, they need to start like looking at quantum and see how they can understand better the universe itself, and at the end of the day, how these technologies can impact their works. And I think there is a lot of effort not only in the industry to develop solutions for the industry itself, but also to create educational paths for people that needs to start understanding this at the point that we reach this. I will not say fault tolerance, but post-NISQ machines that are better than the current ones, and we need people that actually can work with these systems. And if we have more people working on this, probably the evolution of this is the basic of open source, for example, that everyone is trying to test things until someone discovers something new. And we have today OpenAI, we have ChatGPT, but I don't know, 3-4 years later, we have a lot of people doing open source stuff, thinking from the biggest one, Meta or DeepSeek, or I don't know, several players, until someone that is just creative from India, from the United States, whatever, or in Latin America, wherever they are, and they are creating SDKs, they're creating integrations, they're creating AI agents, they're creating, and I don't know, new startups full from AI. I don't know, but Y Combinator, I think probably 90% of the startups that are going through Y Combinator have AI integrated in their systems, or they are related to AI in the business sense. So the workforce needs to be prepared for that kind of thing with quantum. Again, I'm not trying to contribute with the hype, but I would say that we will have this ChatGPT moment with quantum in a smaller scale, and we need to be prepared for that. The business as well. The one thing that Boston Consulting Group shared, I think 2 years ago in a Q2B event, is that probably the companies that are working today with quantum computing will have 90% of the will keep the 90% of the value of the whole journey of quantum computing in the next, let's say, 10 to 15 years. Because if you're creating things now, you will have access to devices, you will have access to the small amount of talent that are available. But when this reach the peak of usage, the talent will not be that big. You will not have access to all the devices because they will become expensive, and your people is not trained enough. So it's really costly to like trying to have the same technology that another company started working, I don't know, 3 years ago. So I think this is quite relevant for this chat GPT moment that I think could happen in quantum computing.
Taking that a little further, maybe what is the challenge with the application of quantum technology and just being quantum ready in such highly regulated fields like the banking sector, maybe? Because since this is your area of working, I'll maybe stick to that. What are the challenges there?
Yeah, I think one of the biggest challenge that I'm seeing in the financial sector, I would say with any technology, but for classification or credit scoring, for example, but quantum computing and quantum machine learning will be involved in that, and is already involved in that, is that you need some kind of interpretability for the scoring system. So you need to understand why you are rejecting or approving someone. If you're approving someone, you need to understand, okay, these are the kind of variables that are, I don't know, adding some kind of, I don't know, understanding, let's say, in a general sense, for the model to decide, okay, this person is actually a good future payer, or this person is not is not having the requirements to actually receive a loan. So you have that with, for example, with XUs, you have a feature importance, or you have the sharp values, or you have different techniques that allows you with classical machine learning to understand those things. If you're using just a policy rule based model, you know exactly what are the policies that the person is not, I don't know, is not compliant with. And the banking authorities require that. So not in all the places, but mainly is always asking, okay, how you prove that your system is actually fair and you are approving or rejecting people correctly, and you need to be able to explain that. This is why deep learning is not that used in classification models in the banking sector. They're not using too much neural networks because it's difficult to explain why someone is rejected or not. And in the case of quantum computing and quantum machine learning, you usually need to first reduce dimensionality, because if you have 300 features and you're playing with 10 qubits, you need to reduce one feature per qubit, let's say. So you're using PCA or LDA or any technique to reduce dimensions, or even you can use some neural networks even to reduce dimensions. And then you encode this information, which is already reduced, into circuits, right? So into the qubits itself. So with embeddings, with feature maps, so you have vectors. So how you can explain how this works. So how you can explain if someone is rejected or not, why it was rejected. So my impression about this, and I was thinking about an event, I don't know, was a kind of a workshop that I attended, was related to European Banking Authority. They said that if the improvement of the model is bigger enough, they can sacrifice a bit of explainability, right? But this needs to be demonstrated. But usually, all the banks and financial institutions should reject the creation of models that cannot be explainable. Uh, and this is one thing, okay? So this is something important to take in account. And what is my suggestion? Not use quantum machine learning or deep learning to decide whether someone is good or not. Use this as a second layer. So you have people accepted, people rejected, and from the rejected ones, you can say these people is already rejected, and we know that they were rejected. So the justification is there, but you can reanalyze these people. Let's say the gray area with new techniques, with deep learning, with I don't know, generative AI or whatever solution you have in mind, or quantum machine learning, and see, oh, I was approving 20% of this portfolio or this list of users. I can approve 15% more or 20% more, and with great accuracy. So I think this is an example, or you can integrate your classical machine learning model, the output of your quantum machine learning model. Let's say you extract a probability or a score from a quantum machine learning model, and this feature is integrated with the main one, with the classical one. So there is a lot of combinations. The other challenge is that you have these highly regulated scenarios that the data cannot go outside the bank, right? Sometimes they cannot go outside the country. So you need to first try to understand how you can encode the data in a way that you can send that information to a external system. Because computing is available everywhere, but quantum computing is not. So you cannot just, if you're a bank, perhaps you can like actually buy a computer, a quantum computer. It will be really expensive, right? Between, I don't know, starting from $10 million and onwards. But but could be really expensive to do experiments or trying to start looking how this works internally. So I think the software companies needs to deal with the encryption, or let's say the encoding of the data, in a way that the only thing that goes out is something that is not meaningful for a human, right? It's not something that you can decode. It's not something that you can trace. It's not something that will be something interpretable for third parties. And these are in my viewpoint, these are the two challenges. There are other challenges like adoption, like people that are not truly understanding what is quantum computing, how this works, how this can have a greater impact, um, like risk averse, right? But in the sense of regulation, I think these are the two main things. And again, like we have now in Europe the AI Act, which is trying to regulate very heavily the process of the AI in different institutions. At some point, we will have the same with quantum. I guess it's not there yet, but will come.
Taking a different tangent towards the entrepreneurial side of things, when you're working at such a intersection of various fields, because quantum technology inherently it welcomes a multifaceted background, right? uh, when you're working in such domain and are wanting to begin a venture at the bleeding edge of such a technology, how do you even begin as maybe a young person, or whatever age, I mean, a young person in terms of their journey in the quantum domain in the field?
It's a great question because usually I receive that kind of messages, let's say 5 or 6 times each week from different people in the world, trying to ask me how I can, I don't know, being involved in quantum, how I can learn, what is the path. I always tend to recommend what I'm biased with. It's my own history, right? It's my own journey. It's like I didn't start reading like complex books or trying to go through these rabbit holes about understanding everything because it's really complex at the beginning. This Nielsen and Chuang book and this complex mathematics and linear algebra and some counterintuitive things that you need to learn is not that easy. So I start from something that I knew. I knew how to code. I knew how to use Python. I know what how the libraries works and how we can play with machine learning. So I start coding directly. And the Qiskit, for example, in the case of IBM, did a great work, and also Penny and also you have CQ, and you have Q Sharp, and you have different libraries available for anyone to start doing these experiments in let's say, minutes. There's full of information in YouTube. There's full of Udemy courses. There are full of Coursera information and courses as well. Qiskit permanently launch new videos explaining how this works, how you can use Qiskit, and how you can, I don't know, understand a little bit better how this programming system works and how you can actually impact real quantum computers or just simulators. So for someone that is already a data science or someone that just know Python, is should be really easy to start playing with. I'm not saying that he or she will understand this right away. So, but my feeling is that someone that is doing something rather than just reading, they will try, this will ignite their curiosity right away. So trying to understand why they receive a worse AUC or better AUC than my, I don't know, classical model. How these boxes and in lines are circuits and how they work, why they have different rotations or we have different gates, how these gates works. So doing, but or by doing, you start learning and trying to discover how this works. And then you can jump to other type of tutorials, actually books, and practical books even, which is my attempt as well. As like half of my QML Unlocked book is with code specifically for that. But my recommendation is you please don't start looking at master's degrees or PhD's degrees right away. I think all the people say, oh, I need to pay a master degree. Eventually, 20 years ago, when the internet was not so full of information or not so available for everyone, you need to pursue a classical career, right? So you need to just do your first university degree, then you go to a master degree, and then you have your PhD if you want to go through this complex field. But now you have information everywhere, and you can do some meaningful things in days. I'm not saying that this is easy, completely easy, but you can start really easy. I think this is fair to say. But then you need to start looking at, okay, how this works, and not playing blind, trying to understand exactly what kind of things are being done in every line of code. And also expanding a little bit the concept of software engineers or data scientists, I think the quantum field needs more people that eventually are not technical. So just people understanding the business, how they can help doing marketing for this business, how they can, I don't know, share information or do the outreach, right, of several companies in terms of how they can be, these techniques can be easily explained. So I think when we're not looking only for people that they are technically capable to do stuff, but also people that can do business with quantum technologies, and they can understand a little bit the basics. So I think for someone that wants to follow a path of quantum machine learning, I would recommend to start by coding right away. And also, when you're trying to discover what happens with this code that you're making, jumping to different, let's say, different books. And those books some of them are quite good. I recommend some books from Maria Schult. There are some books related to more techniques itself, the more technical ones, or the more theoretical ones. So you have different options available. I put a lot of posts in my LinkedIn about these subjects. And also I have my blog, is a Quantum Fighter. And you have code there from starting from scratch, so you can start learning without any previous knowledge, assuming that you have some Python experience.
Another very relevant question then becomes, when is a PhD necessary and when is it not, and how do you figure out if for you it is required and necessary or not at all?
I think there are people that are saying in the field, there are people in LinkedIn, or people discussing in several, let's say, scenarios. They're saying, oh, you cannot oversimplify quantum in general, the quantum field. So they will say not anyone can jump and do something meaningful. I'm against that, because I think some people have the right intuition from the beginning, and they can understand things faster, and they don't need a PhD. But I respect a lot the PhD experience. I think there are roles, like I said, from marketing, business, technical stuff. All the companies and the industries need several roles. I think, if I don't remember, if I'm not mistaken, I think Quantum Flagship defined some roles that are like they're appearing in the time about quantum computing. But I respect a lot what PhDs are doing. I have my own PhD, and I think I learned a lot. It was really relevant for me to expand the knowledge that I had at that point. But it's not extremely required. So I think people that wants to learn and have the right intuition can add a lot of value to all the companies in quantum, or even, let's say, any industry, and they want to, I don't know, add value from the quantum side or quantum machine learning. I think they can do it right away, and they don't need a PhD. There is a misunderstanding, I guess, for some people that thinks that they need the PhD because just the grade and be respected. Um, that's true in some cases in the quantum field, but to be honest, do the PhD because you really love what you're doing, and you really love investigating, and you really love the quantum machine learning and quantum principles, and how you can add value to the humanity at the end. Because PhD, the approach to the thesis is like you need to add something meaningful for the society. So I think, please don't do it for the grade. Do it because you love it. And I think this is more meaningful. And about the tags that they can say, oh, you are or not a PhD. at the end of the day, your results and your practical, I don't know, outcomes will talk by themselves.
In terms of a career in research, academia, or even industry that is related to such pertaining technologies that haven't fulfilled themselves, haven't completely realized themselves. In such fields, how do you define what metric do you use to define success of a business, an idea, a venture? How do you define it? In what way? What would be maybe decent enough criteria that you can probably utilize to do a half a decent job at giving a shot at trying to define success?
I think the criteria, I think, is a great question. Again, the criteria to success, again, is a little bit biased by my experience, but sometimes, especially in quantum and the field that I'm working in is in quantum machine learning, there is this mix about people coming from the academia. Usually, they are the CTOs of the company or even the CEOs in some cases, and you have other people that are not from academia. They're more from the business side, not exactly commercial stuff, but they are working as technical, I don't know, in technical teams in different companies, and they jump to quantum. My concern is that the academia needs to work closer to the market. For example, I'm seeing regularly papers that are coming with different techniques of quantum machine learning, and they are always using like very basic data sets. They are playing with really small sample sizes. They are not measuring the results of the classification correctly, and this is not one. There are dozens of papers every month that are doing, like, there is the loophole of doing the same. In the academia, this could be something acceptable because they are proving something, let's say, in a scientific method, with a scientific method that shows that they have better results, right? For example, they do a quantum kernel method that surpasses a classical SVM. But you are comparing this with the state of the art of the classification in the market with XGBoost. You are comparing the classical model with all the parameters already optimized or not. Why you are using accuracy to measure the outcome if the data set is imbalance? So if you have 90% of one class and 10% of the other, if you predict all of them as a certain class, you will have 90% of accuracy. This is not good for your outcome. You need to use AUC or using KS or using any other measure that actually gives you a sense of how good is in discriminating the two classes, this model. So my concern is that where some people is spending a lot of time using, I don't know, government resources or even university resources to trying to do something in a way that could not scale. Not all of them can scale to the business. So I think it will be very good, in my viewpoint, in the future, that people that are working in the academia, trying to get involved really quickly, even pushed by the university to do that really quickly to the market, and trying to play with real data sets, bigger data sets, and see what they can do. I think this will accelerate extremely all the manpower or workforce that we have available at the beginning in the academia as well, and trying to expose this to the market faster. And they will discover that certain techniques are not scaling at all, and some others can scale. I will not say fast, but perhaps they have a future. And this is exactly what I tried to do in the last 4 years, 5 years, trying to always test my stuff in real scenarios. And I'm encouraging every time different fintechs or companies that I will say, okay, you don't need to start paying anything. We can start just exploring, see what happens, and then we can scale. So I will not say, I will not recommend to do this for everyone, but because you always need to charge something because it's your time. But from the academia, I will recommend that expectation of success that you mentioned somehow should be related to the how scalable your solution could be in real scenario.
We talked a little while back about how the the entry barrier in the quantum domain is maybe more so dependent upon you being willing to curate your specific stack of skills in relation to your own predisposed background in whatever technical field you have. But maybe taking it another step forward, for undergrads, right, who want to penetrate in the quantum domain, or even master students, getting an internship, cracking a job interview, what sort of experience, like you do not have any prior experience, any internships or anything, what sort of projects can you build? What sort of particular, well, work that you can do that would reflect good on your CV and be able to convey your particular subject matter expertise in a way that is able to make your foot step through the door?
Yeah, the entry barrier that you are describing about, okay, if I really want to, I don't know, become involved, let's say in the quantum field, in the startups or any kind of company related to quantum computing, how I can do it, how I can the, like show that I'm capable. First of all, again, I will come back to the phrase of you need to love what you're doing, not only because you want the job and you want to have the shirt saying, okay, I'm working in D-Wave or working in OQC or working in IBM. It's not just because it's not that. It's you need to love it. But said that, usually some people trying to get involved just do following the tutorial, and I think this is not good. I think it's good to learn, definitely. So putting something in a GitHub repo using Kaggle data sets and showing, oh, I can actually run a QSVM. So, or I can use a kernel training method and then having a QSVM or using variational classifiers. Um, that's fine. That's okay. So it's extremely good to learn. It's exactly what I mentioned in a few questions ago. It's like, okay, this is the way that you can start learning. But trying to do something intuitive from yourself. Trying to share something, okay, I want to play with the kernels in a different way. I want to try to explore a different technique. I want to use a genetic algorithm to create a feature map customized for this data set. I want to, I don't know, combine different kernels and see what happens. This intuition, and I think you can start from tutorials playing with that. This is more meaningful for the market. I think for the quantum startups and people that are trying to work with new talent, it's like you don't need to just be compliant with the tutorials. You need to try to be more intuitive and try to work by yourself, discovering something that could impact the result at the end of the day. Because even in machine learning, it's not only about quantum. You need to have this intuition to keep testing. So is the data set, is the way that I'm encoding the data, is the way that I'm manipulating features, is feature selection, is feature engineering, is the parameters of the model, how many algorithms are available, dozens of them, and what kind of measurement I don't know, use to see if this model is good or not. How is the generalization power? Should I use cross validation? Should I use grid search to test something? So it's an iterative process. You need to have this curiosity and keep exploring with QML, right? So the people that are more intense in that sense, I think, can demonstrate something more, I don't know, relevant for those companies. And of course, some of these companies as well will require some technical, let's say not technical background, but at least technical knowledge, in the sense of how QML works. So you, even if you're doing something good with the code, you need to be able to explain it. And this is not trivial. But I would say that moving the line a little bit further in terms of not following the tutorials, not saying, oh, I can do a QSPM. That's great, but you have the intuition to keep evolving. You have the proactivity to keep doing stuff differently. I think this is I think this can be applicable to other things as well, not only quantum, but I think this is, for me at least, people that are hired. I think this is one of the things that makes a lot of sense for me in terms of hiring someone.
Taking the conversation towards science communication, you yourself communicate a lot regarding such complex subject matter like quantum technology, quantum machine learning. You write a book, you consistently convey your thoughts and opinions and your teachings over your blog, your LinkedIn. I mean, first of all, why do you believe that it is important for an individual to whatever extent indulge in active scientific communication? Like not just consumption, but rather to whatever degree creation, production, procurement, and then the outward permeation of the knowledge that you have procured to your friends, to the internet, to whatever extent and whatever way or form or medium.
I think one of the best ways to learn something is explain to others. When you talk about the path that someone can follow to, I don't know, being involved in quantum computing, I think communicating to others, trying to explain to your mother or your friend or your, I don't know, brother or sister, whatever, is definitely a huge step to understand better quantum computing. When I try to explain a paper or I try to explain in the book how quantum machine learning works or how the, I don't know, different techniques can add value, it forced me to explain something that I need to understand perfectly, or not even perfectly, but at least good enough, right? To be able to explain to others. So communicating scientifically is extremely important. It's really important at different levels. The people that are just creating papers to explain to other scientific people that this is good or not, until, I don't know, conversation around a barbecue. Okay, what you're doing? No, I'm working in QML. So what it means? So you need to start explaining that. If you're able to explain that, you're learning along the way. So I would say that my work is, I'm really passionate about it. So I enjoy every single line of, I don't know, code and also post that I do in LinkedIn. But I love how people get involved. I love how people trying to understand further. I think this is crucial for the industry itself. So more people, if more people get involved, this industry will evolve as well. But also I think that just the exercise to explain to others is a big part of the learning path. So I would recommend to others to try to communicate. What I would say also is that you need to be careful about the hype. Please don't follow like mainstream stuff about, oh, this will change the world in 24 hours, or I don't know, this Michio Kaku, I don't know, saying, oh, the world will change in a few years and everything will be quantum, and how they explain the entanglement in a very, I don't know, science fiction way. So I know that some people can think that, okay, this is kind of Star Trek, right? I have some Star Trek stuff here, so I know what I'm talking about. But at the end of the day, you need to be practical. You need to show to the people what's really happening, and it's not about changing the world in 24 hours. It's making impact in niche cases and keep scaling from that. And I completely, I don't know, involved in what is happening, because I follow every news, every paper that is coming. And I know that we're in the right track, and potentially in a few years we will have really impactful thing in different industries. But please don't follow like my mainstream stuff, because they're not so accurate uh, most of the time.
When people start with anything new in the entire journey of them learning, they often have a little unrealistic expectations from how quick they'll be able to master that particular material. What, according to you, would be a realistic timeline to measure one's progress from the time that they have started learning about the quantum stuff. Like, we can take it different ways. Everybody will have a different rate of progress, surely, due to some personal factors and other different things. But for example, a person has got a background in programming, machine learning, even, and they are starting to learn quantum mechanics. They know the high school level physics and everything, but the in depth quantum mechanical phenomena and everything, that may be novel stuff to them. What would be a realistic timeline for them to maybe use as a yardstick to be able to measure the progress better?
Thing you can have when you talk about realistic, I don't know, outcomes from this learning path or something meaningful, I would say that someone can extract something good in with this background that you are describing, I don't know, in 2 weeks, but meaningful for him or her, not for the rest of the world. You know what I mean? So I think, and this is part of the motivational part. If you are, if I'm saying here in this podcast that okay, you need to wait for a year. Okay, so year for how many things I need to read, how many line codes I need to create, how many books I need to explore deeply, or techniques, or videos, or I don't know. Um, but really, you can have some interesting outcomes in 2 weeks if you have enough time to dedicate to this, of course. But I would say to if you think about working part time, freelance, or even full time in this area, eventually you need probably a year or two, I would say, to actually have experience, be able to code stuff, even testing with your own companies. Perhaps people that are working in data science or software engineer, I encourage them to go to their, I don't know, leaders or technical leaders and say, oh, I want to play with a little bit of, I don't know, quantum computing or quantum techniques that are available in Python. And they can say, oh, that's good. That's a good idea. If you have some, I don't know, 10% of your time or 20% of your time to dedicate to that, that will be fine. Um, and then can start learning even within their work, not only in their free time. So I think being very practical, not only theoretical, but really practical about how they can start learning about it, I think they can have something in 2 weeks or a month. But to have enough experience to fully dedicate their time in quantum, probably a year or two, with some courses, some certifications, but especially more experience about, okay, I actually implemented this in 2, 3 kind of problems. And some of them are working, some others are not, but I learn a lot, and this is enough. But I would say a year or two. Yes.
What would be your advice to what would be your advice to you when you were starting out your own venture? Falcondale, you started Falcondale, and the entire thing in the financial sector, trying to implement QML and everything. There invariably are things that you realize that you could have done more efficiently and effectively, but that again was part of the entire learning curve. But needless to say, what would you recommend or advise somebody who's right now at your place as you were when you were starting with your venture?
It's an excellent word. It's an excellent question. I was thinking about what will be my advice, and probably since I love this too much, I will spend the same time that I spend in different experimentations and work and trying to reach the market as I trying to do with quantum in the last, let's say, 2, 3 years. But what I would say, and I think a lot of colleagues will agree with me, is that keep the expectation low. Learn because you want to learn because, or do experiments because you like to do this. But quantum in these early days, you always expect to have impressive outcomes from nothing, right? So just start coding and eventually, oh, this will be, I don't know, amazing, and I will break the market with this new approach or new algorithm or the new way of coding something. And it's not that fast. So my recommendation to myself will be, I don't know, please don't put the expectation that high. and trying to be more realistic about the outcomes that you can get. And this is not bad. It's just a journey.
What is the most interesting facet, or maybe even the most interesting paper that you have read recently that made you like, okay, right, this is something really exciting that is happening right now in the industry?
I really love what some of the researchers are doing, trying to hit NISC machines. I think this is very exciting for me. There is a Cubo SBM work that trying to work with Pascal machines. There are some IVM attempts, HSBC attempts with IVM about multiple kernel learning. So there are a lot of things, a lot of papers in the last, let's say, 24 months that are not just playing with simulators, which is good, and I'm working on it as well, but also trying to use mixed machines as it is. So my recommendation is, for the people that really wants to investigate this, like every single day, use your newsfeed software. So I'm using, for example, InnoReader, and I put my keywords. So NISC plus, I don't know, quantum machine learning, or NISC plus optimization, or QML, or quantum machine learning. And every morning, I configure also alerts to my email and so on. So every morning I have my full list of papers from archive, from other media, from different journals. So I'm receiving all the information. And usually I'm reading a lot, the ones that are trying to hit NISC machines and test what happens. And some of them, to be honest, are scaling promisingly well, and they are having really good results. And like I said, not doing just toy models, trying to really play with a more realistic data set. So this will be my recommendation.
As the final segment of the show, there's this particular question that I like to ask all the guests that I have on the show. Dr. Xavier, what would be your word to humanity at large?
What will be, sorry, what?
Your word, your message to humanity at large.
So I was hearing the other day something, I think was YouTube, a YouTube video, some like was a documentary, and that they were interviewing someone that is investigating quantum computing here in Spain, right? I think it was Barcelona, and the reporter asked this researcher, okay, what happened if quantum computing is not working? So this just waste of time. And she said, probably if not work, we will learn a lot along the way anyway. So, and this going back to some of my first comments about it, I really love quantum computing, and at the end of the day, quantum, because it's defining our universe. It's a great mystery at the end of the day. Not all of it, but big part of it. I remember a discussion between the Dalai Lama, I think, for in the early 2000s, between Dalai Lama and Anton Sillinger. It's a Nobel Prize in physics, and one of the things that they started discussing is that what happened with this double slit experiment. So it's a we're not well, when we're not looking the particle, it becomes a wave. So what happens? And the Dalai Lama just smiled and said, "This is something that don't want to be discovered." So it's a weird thing at the end, but it's something that defines our humanity, our reality, and my message to the society is actually trying to go to a field, even if it's technical, that's fine. But an objective probably in your life that should be related to things that passionate you, or give you passion along the way. It's not only about, I don't know, having the shirt of IBM, or having a great salary, right? It's also about how these things moves you. Um, Sometimes I work on the weekends, for example. I have 3 kids, and I love my kids, and I play with my kids as well. But I spend time my weekends working in quantum machine learning sometimes. And some people said, why you're doing this, or what you're so late working on this stuff in the weeks, in the weekdays. So I said, because I love it. Some people play trying to see Netflix, or no, play with PS5 or whatever. I love coding and trying to discover something new. And I will, even if QML doesn't work in the future, or quantum computing doesn't work, I will stay there anyway, trying to discover what happens.
Dr. Xavier Mancilla Montero, thank you so very much. I really appreciate you for doing this and having this entire conversation. Thank you so very much.
Thanks a lot for the invitation. I love the conversation, and congratulations for your amazing podcast. Like I said at the beginning, I'm seeing all your videos and they are really insightful. So thanks a lot for your work.
Thank you.